Just briefly, what I would like to tell. I would like to tell about the two projects we have now. One is the MGB2 XC2 in situ wires made by high pressure. Another one, which is not here, not for today, is the hydrogen container for 1,500 bars of hydrogen. And I would like to develop a standard high pressure equipment, microstructure and grain connectivity of back samplers, and melting temperature change during the high pressure annealing, high pressure annealing for the make the positive modification of the superconducting structure, and superconducting wires obtained by HIP on laboratory scale apparatus, and in the longer one by the production equipment, and practical realization of two kinds of HIP process for long wires. Okay, the crucial and important laboratories which we make already in Poland is on the left side, and in outside is on the other side. You see also the collaboration with Bolu in Turkey, in which we have the wires together in iron. Okay, high gas pressure. Why and for what we are going to use it? The first, the densification connectivity of the densification of the materials, melting temperature change, and possibility to solid state annealing in synthesis under high pressure. This is under inner gas atmosphere, fast transformation. And I put some example of the experiments which you can do under high pressure. It's a lot of this one. So the vapor project will be for IPCO, for mercury and thallium family, a lot of things. Argon density, how it changed the argon density with the pressure. So we see how quickly it changed the density of argon with the pressure. So for example, for low temperature 2712 is the left curve. You see 1000 bars, it gives you already 1 gram per cubic centimeter density. And for a typical temperature of the annealing, about 600, 900 degrees, it's about 4,000 bars. It's enough to get 1 cubic grams per cubic centimeter density. And our apparatus, we use the cylinders type apparatus for the gas. And specific things here is the furnace which is inside, which is a special gas trap system, which we use especially for the poison materials, for mercury, thallium, arsenides, and we make the crystallization inside in this chamber. And of course, we can make the annealing of the samples of wire samples. If somebody would like to know something more about this apparatus, then we can discuss later. And there's another apparatus for quenching. If you need to make quench from high pressure, you can use the same system, the same chamber, but you have the rotate this chamber, and you can take out these samples from here, from this furnace, to this side, and you invert the chamber quickly, and you make the quenching from the high temperature. The most used way to get pure nanopowders of the starting composition, starting metals, or starting magnesium, starting boron, is just to also to make decomposition of the hydrides, so H2 with nanoboron. You can decompose under high pressure using ultrasonic high energy head. And you can strip the gases which are on the surface of the grains, and you can exchange the gas which are on the grains by helium strapping, and protected by the high pressure of argon inside. So the material is very, very pure. This is what it looks like. This material after this process. It's enough 5 minutes ultrasonic high pressure to get this very high purity, and the van der Waals walls are condensed the material at the one. Something about the connectivity, as we see here, the connectivity of typical in situ box is quite low, and for our HIP we can obtain much higher packing factor and grain connectivity, and this gives us possibility to to increase the density of the material in the wires, especially in the wires. And how it changed the characteristics, resistance characteristics with the heap. You can consider three kinds of heaps. One is the heap without the pressure. It's one bar open container. This one, blue one, and then one is the with a container which is open, but high pressure we use for as a gas or around. It's the wire open without the closures of the end. And another one is a totally closed wire, so you get a much lower resistivity with much higher density, of course, of the material. And also in the resistance, you see the difference. And how it is in the structure, you can see in one bar is a lot of porosity, and it's open. In open heap, it means just the dense argon around the material. You have the density which is not very high, but you see all the time the porosity. The heap sealed is much better. You see this very low porosity. And how to decrease the intergrain distances. For example, here in the left side, you see our typical ex-situ in-situ wire. This is our project. So inside we have in-situ material, ex-situ material is out around, and the reaction between ex-situ material and copper, the conditions we have under high pressure, is not very good, very big. So we can use this one as a typical process for the densification of the wire cores. This is one core wire. And you see the experimental for this one is made in the deformable container, and after the heap you can see how it's deformed. This is some example of the heap made on the wires prepared by Minister of Bulu, Turkey. It's in iron, and as you see here, in one bar is diameter 0.98. After heaping just annealing at 1 bar, and in 0.8 gigapascal is 8,000 bars. Is already like this, and structure is, you see in the structure difference of the structure, and on gigapascal also the diameter of the wire is much lower, and structure is like this. So it means there's less and less voids. 1 second, I don't know. Okay. Now the phase diagram I will change for the elements. We see that magnesium starts to melt at high pressure into higher temperature. This is here on the left. You see the low pressure, ambient pressure is 650 degrees, and with 15,000 bars is melting temperature of magnesium is about 730, and for iron, for example, is going down. And after this, we can make the DTR of our system with magnesium diboride. And what we observe that this curve, the line between the solid and liquid phase here is changed the place. So you see another space for annealing. This gives us possibility to anneal in the solid state. And then we can get much lower grain diameters and better compactness of the materials on the grains. And this is a typical curve for annealing under high pressure for the wires. We make in 1 gigapascal pressure in argon, close wires. And so we make here like this, that we go to certain temperature, 570 degrees is here, and we keep for half an hour, and then increase for short time for close the melting temperature. Here is about 720 in 1 gigapascal, and then we keep it for some days to produce the compact material. Up to now, we know two generation of NGP2Y by this technology, by powder in tube. The first generation is in situ materials produced in the metal shield, and another one is the AMD, intermagnesium diffusion, and advanced intermagnesium infiltration. Both names consist of the same technology. Okay, this is our in situ ex situ patented method for obtaining the superconducting wire without the naive barrier. So you see in typical wires made for example by hypertech insights, they use the naive as the barrier and the copper outside or model or something like this. Or okay, and the inside we have in situ material. In our case, we use the in situ material inside the same diameter and outside the ex situ barrier. And then this copper or mono or something which is compacted, and the structure of this you can see inside is in situ material down there, and here is ex situ material and the copper. This after annealing at the high pressure, so you see any reaction between the ex situ material and copper at that moment, and this is the longitudinal direction. You see the in situ material inside, the ex situ just on the surface, and the copper or mono or the material with the copper with good conductivity and good electrical lower resistance. And there's the typical wires which you obtain by drawing and extrusion first. Okay. This is the same, but it's just to see that this the fill factor of such a wire with ex situ in situ is much higher. It's 0.8 equals 0.50, and this naive-free wire is much cheaper than the wire produced with an naive. Naive is the most expensive material in the 1 meter of the wire. This is how we produce the multi-core wires from this one, ex situ in situ one. This is for the samples, which we heap short samples. We use the additional Teflon type to put around to against the scratch which are on the wires. But it's only for the laboratory scale. And this is how we use our high pressure equipment and the furnace. Preparing the furnace and the compressor up to 15,000 bars, which is connected to the chamber. As this is quite old results, but I would like to show on the example of this how it's changed the JC for typical hypertech wire heaped at that condition 1 gigapascal and increase with up to 780 degree. 22 minutes, we go to very good results. So you see that how it looks this same wire. Without the pressure, typical ambient annealing is with the pressure. So we see 100 amps per square millimeter is here limit. So we can increase up to several thousand amps per square millimeter at 8 Tesla here. Yes, you see for 14 Tesla, 13 Tesla, you can get 100 amps as applicable JC current for this material. And the pinning force is also increasing so much. This is another example of the wire obtained from User Bolu. It's very good also. It's in iron. For the same is why you see that one bar annealing is here, and the annealing in the high pressure 0.8 gigapascal can obtain very good results. So you see, you can get 100 at 9 Tesla. So we make it, of course, the best is to make the annealing in the liquid, not in the gas, because gas can penetrate into some little space in between the shields of the wires. So we try to do this short samples in the liquid. So we put the wrapping in the container with stainless steel, and we put we put the samples inside, and we make something like this. So for the measurements, for some samples, just to test the material, it's enough. And we use the eutectic as the liquid. So this, for example, this is the kind of liquid which we use as a liquid for this material. And this is the typical hypertech wire, NGB2. And you can see how it changed the structure and the dimension, the diameter of the wire after 1 gigapascal heap, and the parameters, the JC of this wire. This is again one example of the monocore in situ MGP2FA wire made by Initial of Turkey, Bolu in Turkey. And you see, without the high pressure, we get something like this. And after using the 1 gigapascal in liquid, so it means that in the eutectic, you get very low diameter here, and you see how it changes the structure of the material. And of course, the filter current is increasing here. There is some problem with 1 bar here. I don't know why. It's getting very high at this moment. We have to make some verification. I don't know what's happened. Maybe some stress from the iron. I don't know. This is an example of the. We would like to show how it changed the density of current. For example, for 10 Tesla, measured by the contacts methods of all of this. So we see how it's changed with the pressure. So we have the pressure of normal pressure, and then we increase the pressure. We see at 10 Tesla how it's increased the JC. So several hundred. So it may be 5 times bigger JC we can get after heaping. And for 20K, it's also better, but not as good as it was in the 4.2, but it's also much bigger. So we can obtain 100 applicable current at 4.5 Tesla. And it's also a very interesting thing, which we can find that for monocore wires, in using the FS sheet AMCO one is produced in Unipress, the 1 gigapascal. And we see that if the monocore diameter is bigger, you see the wire, the diameter of the wire. So you see the lower JC. So if it's going to the lower diameter of the wire by drawing or by extrusion, you get much higher JC. So it's another way to increase the JC in the wires, in iron wires. So I make it very quickly because it's short time. Another one is AMD. It is a typical way from before the synthesis. And after the normal, everywhere now, you have the voice inside, you have the empty space in the core. And when we use the heap, you have something very interesting. It means that this core is collapsing. It's the core, the niobium around. This niobium around is niobium, which is here with the hole. It's after the heap is collapsed. So you have the wire which is dense and it's very strange. So it means it's very easy to operate after this. Yes, after this. So you see here, there's no empty space. So you need some better technology to keep more round cores, yes. So for future. And this is the experiment we make with the colleagues from Italy. We put the same as Bolu made here. So we put another direction. We put the 3 tubes, and inside there is the boron, and the sheet. The sheet was the titanium here, quite hard one. And they try to make the low weight samples of the superconductors, and it is very good because we got very nice line of the material after reaction, and then in ambient pressure they got something like this. They have this empty space around, and the material which is reacted, and also inside something which is not totally reacted, is pure boron. And then after the heap, you get almost good here, but it's not enough pressure to 1.1 gigapascal pressure. At that temperature, it's not enough to completely surrounding this inner part. So it's okay. This is something that's very interesting. That when you make the annealing of the, for example, typical hypertech commercial wire, we can get denser and denser material using heap, and here we can observe how it changes the structure, cross-section structure of the multicore wire and the multicore. As the lower and lower dimension, and if you see the JC how it's changed. You see that after 210 minutes, not 20 minutes, 1 gigapascal, at approximately 210 minutes, the JC increase, for example, for 9 Tesla, you see that how it's increasing the JC from this point to this point. So it's almost 5 times higher JC you can get just using longer time for heating. So in the future, it's important to keep long time this heating process for long wires. And another is another type of technology. We try to make the lamella shape inside. This is some complicated method. We use the drawing, slow drawing with low temperature, 520, 70 degree, and then you get the lamella structure, which is very important to give a higher JC than normal one. And this is about some additives. We put up rare earth additives to this. We see that with the carbon always disease drop is lower, but we put nano earth additives, for example, cerium or neodymium get much higher TC. And JC also is very important for higher temperatures, because at high temperature you can increase the JC at close to the
You have
critical temperature.
1 minute.
Okay, just going to show this apparatus for longer wires. This is the laboratory. This is the first our system for making the longest wires, and then we use the cylindrical alumina oxide container, crucible, and chamber to produce the wires in the inside in this chamber. This is how it looks like. The system for this is the eutectic. So we have the eutectic here, the coil, and the pressure pressing system. And then after the pressing, we can get. This is the system with tungsten carbide. And this is the first one. The last one is this alumina oxide, stepped by yttrium, and we got very high density of the wires. And density, we used 1,000 ton method samples. And another way, this is this one was made in the liquid in eutectic, different kind of eutectic we put around here, and this last one is made in the gas. So you can see the typical compressor here with the argonium and 2 chambers connected by the heater inside, and you move the wire from one chamber to another chamber. And this is the laboratory scale. It's not very long wire you can obtain by this method, but actually we transformed this to the new system, in which we have the system which the coil is inside, the wire is going out by one side, coming back to the same side, and then the same process you can get, long process you can slowly get the wire, long wire, 1,000 meters of the wire. This is our project on the end. We have to finish this one, and it will be on the middle of the next year. So this is preparation. And okay. And maybe I will leave this one for the Tomek. He will present today the first results about MGB 11. Boron 11 is maybe could be adapted for the plasma generator as a demo, maybe for the next future. So thank you very much.